All right, this is section 4.2. So two events are independent if the occurrence or non-occurrence of one does not change the probability that the other will or will not occur. Like rolling a 5 on one die and rolling a 2 on a second die would be independent of each other. Two events are dependent, or rolling a 5 doesn't impact the probability of rolling a 2. Two events are dependent if the occurrence or non-occurrence of one does change the probability that the others will or will not occur, like drawing an ace and then drawing another ace in a deck of cards. Getting an ace on the first pick impacts the probability of getting an ace on the second pick. So the rule in general is if you want to do two things or more than two or more things at the same time, you multiply each individual probability like this. Let me turn on my pointer. Like this. Probability of A times probability of B. For both independent and dependent events, what you can do is if you want probability of A and B, it's a probability of the first thing. Now, this is fancy notation for basically saying the probability of getting A given that B happens. So if it's picking an ace and then an ace, it would be the probability of an ace, and then probability of an ace given that you get an ace. So you can read all of that. And basically the same thing down here. You could switch the B and the A around. Probability of B times the probability of A given that B happens. On the next slide, you're going to throw two fair dice. What is the probability of getting a 5 on each? So probability of 5 on first die, probability of 5 on second die. That would be the probability of 5 times the probability of 5. That's 1/6 times 1/6, or 1/36. Now over here, I actually listed using a table what's considered the sample space. So all of these in here, each pair is a possible thing that could happen, a possible outcome. So if you find the two 5s on here, it's only 1 out of the 36. If you count all of these up, it's 36. So 1 out of 36 chance. You're going to draw a card from a well-shuffled standard deck of cards. Keep that card out, then select another, drawing two aces. So this is what we're trying to do, an ace on first, an ace on second. So we break it apart. Ace on first and then an ace on the second, given that or imagining that we got an ace on the first pick. So you can read that. In other words, we assume we get what we want on the first one. So it's 4 out of 52, 4 aces out of 52 cards, times 3 remaining aces out of 51 remaining cards. We assume we get an ace on the first pick, so there's one fewer ace and one fewer card to choose from. So that's 12 out of 2,652, or about a 0.0045 chance. It's so low because, again, it's out of all 52. You're not like dealing it out to people that it changes the odds. The multiplication rules apply whenever we wish to determine the probability of two events, or two or more, together. Together we use and. Usually in a problem we want an ace and an ace. So before you use the multiplication to compute the probability of A and B, you must determine if they are independent or dependent events. Here's what we mean. We're going to have you try this one right here. Adam is 55 years old, so why don't you give that one a shot? And now try this exercise number 2. So continuing on, the multiplication rule extends beyond two events. So basically this is saying that if you do more than one, you can still multiply. So if you're doing tossing a coin, rolling a die, and drawing a card, if you want to get a head on the coin and 3 on the die and a diamond, it would be 1/2. It's probability of flipping heads. 3 is 1 out of 6 probability, and a diamond is 1 out of 4. It's 1 out of 4 of the suits, so it's 1 out of 48 to do all three, this and this and this. Another possibility we must consider is if one event or another occurs. So if we're going to shade in these Venn diagrams to illustrate the difference between A and B versus A or B, A and B would be this middle section. I call it the football shape section. That's A and B, whereas A or B would be all of this. So it includes that middle, that football shape in the or part. Notice that the condition A or B is satisfied by any one of the following: any outcome in A, any outcome in B, any outcome in both A and B. So right here, I'm going to ask that you decide whether these involve the and or the or combination. It's going to be really tough. You got to actually have to read the problem. Are you in an and combination or and/or combination? That's something you have to decide. For instance, if you want to draw a jack or a king on a single draw from a well-shuffled standard deck of cards, is it possible to draw a jack and a king on a single draw? No. But if you want to draw a king or a diamond on a single draw, you'd have to consider the overlap. There is the probability of a king, there's also the probability of a diamond, but there's also the probability of the king of diamonds. So there's overlap. If you want to look at that as a Venn diagram, okay, over on this side I have all of the diamonds. Here I have all of the kings. The overlap would be the king of diamonds. So if we were just to do 4 out of 52, all right, so these 4 out of 50, I'm sorry, these 4 out of 52 and these 13 out of 52, we would be counting the king of diamonds twice. So within here and here, we would actually have this card twice. So we remove it once. Okay, that's to get rid of the overlap. So if we were to add, that's 17 minus 1, 16 out of 52. It's a 4 out of 13 chance to pick a king or a diamond. Two events are mutually exclusive if they cannot occur together. In other terms, events A and B are mutually exclusive if the probability of A and B occurring are 0. Like the jack and a king on a single draw cannot happen, so they're mutually exclusive events. If you know two events are mutually exclusive, like PA or B, you can just add the probabilities together. Like red or green. You could just add those together. But if they're not mutually exclusive, like drawing a king or a diamond, you have to remember to subtract out the probability of the king and diamond in this case, or in that example, so that you get the proper probability. So mutually exclusive, you just add. If they're not mutually exclusive, you have to make sure that you get rid of overlap. Don't count things twice. So, as an example, if you're playing Monopoly and want to throw a number larger than 8 in order to land on one of your properties and pass go, what chances do you have? So, what are the numbers? All right, so is it possible to throw a sum of 9 and a sum of 10, not at the same time? So that means the events are mutually exclusive. Okay, so because they're mutually exclusive, we can just add the probabilities of anything larger than 9. So that would be the probability of a 9, 10, 11, or 12, just added together. If you wanted to, you could go back a few pages and look at the dice in the table, and you could see that it's 4 out of 36 plus 3 plus 2 plus 1 out of 36 equals 10 out of 36, so about a 0.28 chance of rolling something that is larger than 8 to get past go and land on one of his properties. As another example, this is a two-way table showing the political affiliations at the Rubber Ducky Company. We've got executive E, production P, and total. We've got Democrat, Republican, Independent, and total. 140 total employees. If we wanted to pick a random employee from the Rubber Ducky Company, what's the probability that we would get a Democrat and then a executive? So for and, we are going, notice the and is not in parentheses, so we're not going to multiply them. This one's just asking us for two separate probabilities. Probability of a Democrat is 68 out of 140, so there's that. Probability of an executive is, 48 out of 140, and that's about 0.343. But, and there they are right there. If you want to compute the probability of a Democrat given that they're an executive, so that means given that they're an executive, so in this row here, what's the chance that they're a Democrat? So in this one, we're going to do 5 out of 48, which goes to a 0.104 probability. Are the events D and E independent? How do you know? So how we can tell if the probability of a Democrat equals the probability of a Democrat given that they're an executive, then they are independent. So we just calculated the probability of a Democrat, 68 out of 140, is 0.486. The probability of a Democrat given that they're executives was 0.104. Because they're not equal, they are not independent. So that must mean that there's some overlap. So compute P and D. So Democrat and executive would be 5 out of 140, so a 0.036 probability. Letter E, compute the probability of D and E using the probability for dependent events. So what that means is, if you go back a few pages, if we want a Democrat and executive, we could take the probability of being an executive, which is 48 out of 140, times the probability of a Democrat given they're an executive. So that's 5 out of 48, and we get 0.036 again, which, if you think about it, was exactly what we computed here. So what do we notice? They're the same. Are the events D and E mutually exclusive? No, because the probability of D and E occurring, so right here, is not 0, so it's not mutually exclusive. P or D would be the probability of a Democrat or the probability of an executive, but we got to remember there's some overlap here. So 5 out of 48. These 5, I shouldn't say 48, 5 are the overlap of these two rows and columns. So we're going to do the probability of a Democrat, 68 out of 140. Probability of an executive, 48 out of 140. So that's Democrat or executive. But right now, if we did that, we'd be counting these 5 people twice. So we got to remove one of them, or one set of them. So one set of 5. And we get all this down here. So I'm going to ask you to try, same table, okay, try these questions. Should be done similarly to the last few. So I wanted to, real quick at the bottom of here, go over the difference between independent events and mutually exclusive events. Independent events basically mean that the occurrence of one does not impact the probability of the next things happening, the subsequent things occurring. For example, tossing 2 coins and getting 2 heads. How the first one lands doesn't really impact the probability of the second one. Whereas mutually exclusive events, they cannot happen at the same time. It's impossible. Like tossing a coin and getting heads and tails. Can't really do that, I guess, unless it lands on the ridges, but that's really hard to do. So this page here at the top has 8 points to a summary of probability rules. A lot of it is notation. Don't get hung up with a notation, but basically with probability, a couple big things. It's between 0 and 1 or 0 and 100%. With independent events, you basically just multiply the probabilities as they come. With dependent, we always assume that we get what we want, so that's what this little line means, given that A happens, given that B happens. Okay, and then down here, if it's mutually exclusive, there is no way for 2 things to occur at the same time, so the probability of the 2 things occurring is 0. For things that involve the or condition, you would add the probabilities together if they're mutually exclusive. If they're not mutually exclusive, you have to subtract the overlap. So those are some things to remember. But again, don't get too caught up in all this notation. Worry more about if you can actually calculate the probabilities. This bottom here, you can skip. So if you want to X that out, it's not that it's bad. It's just it concentrates too much on notation, and I'm not worried about that too much. So you can X that out. Please let me know if you have any questions, and we'll go over the answers to some of these later on. All right, bye now.